The objective of this lecture is to describe intrinsic coordinates and then to provide examples using intrinsic coordinates. Now, intrinsic coordinates are defined different from the manner in which other commonly used coordinate systems are defined. In order to define intrinsic coordinates, or to describe intrinsic coordinates, consider the following setup. We have a reference frame, define it as A, and a point O that's fixed in A. So O is fixed in A. And we have a point P, which is an arbitrary point, which is moving relative to reference frame A. And the path that's taken by P is described, or is shown, as I draw here. This path is what is called the trajectory of point P as viewed by an observer in reference frame A. Now, at some point along this path, the object, or this point P, is located qualitatively where I've shown it. And the vector from O to P defines the position of P relative to O. Now, intrinsic coordinates are set up as follows, is that at this point P, I'll label P, consider the velocity of point P relative to reference frame A. This is the velocity of point P as viewed by an observer in reference frame A. So let's write this down. VPA is the velocity of P as viewed by an observer in reference frame A. And what we're going to define first is the unit vector along this velocity. So if I take the unit vector along this velocity, that vector I'm going to define as E sub t. So E sub t is this unit vector. Let me give myself perhaps a little bit of room here. E sub t is this vector. Now E sub t, as I said, is the unit vector along VPA. And it's known, or it's called, the tangent vector to the trajectory of P as viewed by an observer in reference frame A. Now, because ET is a unit vector along that velocity, ET can be written as the velocity divided by its magnitude. Now, in order to be able to make this a little bit easier to deal with notationally, we're going to say let this quantity script Vp equal the magnitude of the velocity of P and A. Now, this quantity is what's known as the speed of P as viewed by an observer in reference frame A. Now, what's important to note here is that the speed actually is reference frame dependent. If I change the frame, then the speed changes because the speed is the magnitude of the velocity, and the velocity depends on the reference frame. So even though the speed is a scalar, it doesn't mean that the speed itself doesn't depend on the reference frame. Scalars can actually depend on reference frames, but the rates of change of scalars cannot depend on reference frames, or don't depend on reference frames. So that's an important distinction, that we might construct a scalar, and in this case we're constructing that scalar, or computing the scalar, from the magnitude of a vector, and that vector is a velocity, and the velocity is the rate of change of a position, and the rate of change depends on the reference frame. So the scalar could actually depend on the reference frame, but its rate of change doesn't depend on the reference frame. Now that all being said, we know that ET is a unit vector, and thus we have that ET dotted with ET has to equal 1. So if ET dotted with ET has to equal 1, suppose now that I take the rate of change. So compute the rate of change of ET dotted with ET. Well, that's equal to 0, because ET dotted with ET is equal to 1. So the rate of change of ET dotted with ET is equal to 0. Now, because ET dotted with ET is a scalar, I can arbitrarily differentiate ET dotted with ET in any frame I feel like. So arbitrarily differentiate or compute the rate of change of ET dotted with ET in reference frame A. What do we get when we do that? Well, we get that dET dt in A dotted with ET plus ET dotted with dET dt in A has to equal 0. Now, because in this I've used the product rule of differentiation to be able to compute this rate of change, you'll see that the first term and the second term are the same, because A dotted with B is equal to B dotted with A. So therefore, we can write that 2 times dET dt in A dotted with ET is equal to 0, from which we can write that dET dt in A dotted with ET is equal to 0. Now you'll notice that I now have two vectors. When I take the scalar product between them, I get 0. So what this tells me is that dET dt in A is orthogonal to E sub t. So because dET dt in A is orthogonal to E sub t, I'm going to say let En be the unit vector in the direction of dET dt in A. So if this quantity En is actually known as the principal unit normal to the trajectory of P as viewed by an observer in reference frame A. Now, using that, since En is the unit vector in the direction of dET dt in A, we know that En can be written as the rate of change of the tangent vector in A divided by its magnitude, because that defines a unit vector. And from that, we can actually write that dET dt in A is equal to its magnitude times E sub n. Now look what's actually happened here. We've defined two directions. So two orthogonal directions ET and EN have now been defined. So from this, we can define a third direction. So a third direction that is orthogonal to both ET and EN can then be defined as, I'm going to call it E sub B, which is equal to ET crossed with EN. Now this quantity E sub B is what's called the principal unit binormal to the trajectory of P as viewed by an observer in reference frame A. Now you'll see that the triad ET, EN, EB forms a right-handed orthonormal basis. And is called an intrinsic basis. Intrinsic basis. And the associated system of coordinates is called intrinsic coordinates. So let's write that down. The system of coordinates associated with an intrinsic basis is a system of intrinsic coordinates. Now let's look and see what we can do with this intrinsic coordinate system or this intrinsic basis. So recall that the tangent vector was defined as the velocity of the point P in reference frame A divided by the speed in reference frame A. From that, we can actually write that the velocity of P in A is equal to the speed of P in A times the tangent vector. Now, given the fact that we know how the tangent vector changes, because we've actually done that in this last result here, we know that the rate of change of the tangent vector lies in the direction of the principal unit normal. Let's take the rate of change of the velocity in reference frame A. So the acceleration of P in A, which is the rate of change in A of the velocity of P in A, is equal to the rate of change in A of the speed in A times the tangent vector. Now, let's take the rate of change. It's a product, right? But the first factor of this product is a scalar. So I can take the rate of change of the speed in any frame and I get the same result. So I get ddt of Vp in A times the tangent vector plus Vp in A times det dt in A. But det dt in A is equal to the magnitude of det, dt, and a times e sub n. So that tells me that the acceleration of p in a is equal to the rate of change of the speed in a times the tangent vector plus the speed times the magnitude of the rate of change of the tangent vector in a times the principal unit normal. And you'll actually see that there's no component of the acceleration in the direction of en. Of EB, in the direction of EB. Now the last thing I want to discuss before we go into the examples is there are two planes that are actually of importance here. The plane formed by the vectors ET and EN is called the osculating plane. While the plane formed by the vectors ET and EB is called the rectifying plane. So you can see that the acceleration lies in the osculating plane because it's defined by ET and EN, and it does not lie in the rectifying plane. So now let's go back to the diagram and let's finish what's in the diagram. So the diagram can be completed. Is that this direction is EN, and then this direction is EB. So we can now draw everything together to be able to describe intrinsic coordinates. So here's the trajectory of P in reference frame A, and here's my point P. Here's the velocity of P in A. The direction along that velocity is my tangent direction. This is my tangent direction. It's also called the tangent vector. This is my point P. This direction is the principal unit normal, and the cross product between them is the principal unit binormal, and this is my point P. And then once again, for completeness, I can actually lay down this schematically, this reference frame, which has this point O, and I have the vector from O to P, which is the position of P relative to O, and O is fixed in A. And this path that is subtended by this point is called the trajectory of P as viewed by an observer in reference frame A. So that's the theory of intrinsic coordinates. Now let's do an example to show how we can actually use intrinsic coordinates to solve a problem. So in this problem, I have a particle that moves on a circle, except for, in this case, rather than defining all my distances from the center of the circle, I'm going to define all my distances from a bottom point on the circle. I'm going to call this point O, and here's my point P, and I'm interested in the motion of P, and here's the vector from O to P, and this distance is going to be r, and this angle from the rightward direction is going to be theta. Now, for this particular problem, r is going to be equal to the sine of theta. That defines a point on the circle. Given an angle theta, I know where I am on this circle. Now, in order to do this problem, we're going to use intrinsic coordinates, but we're going to use them in an after we've defined another coordinate system, and then we're going to convert everything into intrinsic coordinates to show how nicely the velocity and acceleration can be expressed in terms of those intrinsic coordinates. So the objective of this problem is to determine the velocity and acceleration of point P as viewed by an observer fixed to the track. And this here is my track. It's this circle. This is a track. And it's a circular track. So I could say a circular track. And we'll define that as T. Now, in order to do this, we're going to start the same way we always start, which is we have to define rotations and frames. So we have one rotation in this problem, which implies that we need two reference frames. The base reference frame is the track, which I denoted already as T. The first rotating frame is now, I'm going to define it and then we'll explain how it works, is the plane formed by the direction, say the directions out of the page and OP. So now let's write this down. T is equal to the track, which is the base reference frame. I'm going to put the origin at O. I'm going to put, now I'm going to do this in a little different order from what I often do it, but I'm going to put EY along OP when theta equals pi over 2. So that's actually the direction kind of upward in this diagram if you want to look at it that way. I'm going to put EZ out of the page, and then I'm going to put EX to equal EY crossed with EZ. The second reference frame, which I'm going to call A, is going to be now the EZ OP plane. And you remember that I defined it already to be the plane formed by the directions out of the page and the direction OP. That is now the EZ OP plane. So the origin of the coordinate system is again going to be at O. I'm going to put ER along OP. I'm going to make EZ, little ez, equal the same thing as big EZ. And then I'm going to make E sub theta equal EZ crossed with ER. Now once I do that, I actually can define very nicely the position of P relative to O. So let's just do that over here. The position of P relative to O is then going to equal RER, which is going to equal sine of theta times ER. So now I have a nice expression for the position of P relative to O. So once I have that expression, let's compute the velocity. We're going to do this first part the same way we normally would, which is using the transport theorem. So the velocity of P as viewed by an observer fixed to the track is equal to the rate of change as viewed by an observer fixed to the track of the position of P relative to O, which is equal to the rate of change in A of the position of P relative to O plus the angular velocity of A and T crossed with the position of P relative to O. Now let's take the first term in this transport. The rate of change in A of the position of P relative to O is equal to theta dot cosine theta times ER. I also know that the angular velocity of A and T is equal to theta dot EZ, which implies that the angular velocity of A and T crossed with the position of P relative to O is equal to theta dot EZ crossed with sine theta ER, which is equal to theta dot times the sine of theta times E sub theta. So from this, I obtain that the velocity of P as viewed by an observer fixed to the track is equal to theta dot cosine theta ER plus theta dot times the sine of theta E sub theta, which I can rewrite this by factoring out the theta dot, and I get cosine of theta ER plus the sine of theta times E sub theta. So now is where we're going to actually start transforming or molding this into intrinsic coordinates. So first, let's compute the speed. So the speed of P as viewed by an observer fixed to the track is equal to the magnitude of the velocity of P as viewed by an observer fixed to the track. Well, what's the magnitude of this vector? Well, it's equal to theta dot, if I assume theta dot's positive, times the magnitude of the vector that's in the parentheses. But the magnitude of the vector in parentheses is 1 because it's just got two orthogonal components of cosine and sine of theta. And if I take the sums of the squares and take the square root, I get cosine squared plus sine squared equals 1. The square root of 1 is 1. So this gives me theta dot. So that's the speed. So that tells me that the tangent vector to the track, which is equal to the velocity of P as viewed by an observer fixed to the track divided by the speed as viewed by an observer fixed to the track, is just equal to cosine theta ER plus the sine of theta times E sub theta. Furthermore, I can also say that the velocity of P as viewed by an observer fixed to the track, which is equal to the speed as viewed by an observer fixed to the track times the tangent vector, that's what I derived when we derived intrinsic coordinates, is equal to theta dot times ET, because the speed is theta dot and the tangent vector is defined as ET. So now I have a nice compact expression. So you can see I have two expressions here for the velocity of point P as viewed by an observer fixed to the track. The first one is in terms of cylindrical coordinates. The second one is in terms of intrinsic coordinates. And you can see that the expression in intrinsic coordinates is significantly simpler from the expression from this expression in cylindrical coordinates. So I get this nice compact intrinsic representation of the velocity. Now from this we can actually start computing the acceleration. So next, what's the acceleration? Well, we know that the acceleration of P as viewed by an observer fixed to the track is equal to the rate of change as viewed by an observer fixed to the track of the velocity as viewed by an observer fixed to the track. But that's equal to the rate of change as viewed by an observer fixed to the track of the speed relative to the track times the tangent vector. So now again we can use the product rule of differentiation, and we get d dt of Vp in t times Et plus the speed as viewed by an observer fixed to the track times the rate of change of the tangent vector as viewed by an observer fixed to the track. So now let's go ahead and take the rate of change. So we know that the rate of change of the tangent vector is viewed by an observer fixed to the track. Well, let's go back to the expression. You see that the tangent vector is written in terms of the basis ER, E theta, EZ. So this is going to involve a transport theorem from A to T, just like it would for any vector, which is expressed in a basis fixed in a particular frame. In this case, the tangent vector is expressed in a basis fixed in reference frame A, so I'm going to apply the transport theorem from A to T. Now, what is the rate of change of the tangent vector in reference frame A? Well, given the fact that the tangent vector is cosine theta ER plus sine theta E theta, this is equal to negative theta dot times the sine of theta times ER plus theta dot times the cosine of theta times E sub theta. The next term in the transport theorem is omega AT crossed with ET, which is equal to theta dot EZ crossed with cosine theta ER plus the sine of theta times E sub theta, which is equal to, well, EZ crossed with ER is E theta, and EZ crossed with E theta is minus ER. So I get minus theta dot sine theta ER plus theta dot cosine theta E theta. So you see that these two terms in the transport theorem actually give me the exact same result. So what I can do now is let's write this a little bit differently so that we can actually see this in a slightly different way. Suppose I factor out theta dot out of the first term. If I factor theta dot out, I'm left with minus the sine of theta ER plus the cosine of theta times E sub theta. Omega AT crossed with ET then, because it's the exact same thing, gives me theta dot times minus the sine of theta ER plus the cosine of theta times E sub theta. So therefore, the rate of change of the tangent vector as viewed by an observer fixed to the track is going to equal 2 theta dot times minus the sine of theta ER plus the cosine of theta times E sub theta. And what we need here is we need to now express this in terms of intrinsic coordinates. So we know that the principal unit normal is going to be defined as the rate of change of the tangent vector as viewed by an observer fixed to the track divided by the magnitude of the rate of change of the tangent vector as viewed by an observer fixed to the track. So what's that equal to? Well, that is going to equal, well, let's compute the magnitude first. So let's go over here and compute the magnitude of the rate of change of the tangent vector as viewed by an observer fixed to the track. Well, I've got 2 theta dot out front, and I've assumed theta dot is positive, and then it's the magnitude of the vector that's in parentheses. But the magnitude of the vector that's in parentheses is 1 because sine squared theta plus cosine squared theta is equal to 1. So this is just equal to 2 times theta dot. So then the principal unit normal is going to equal minus the sine of theta ER plus the cosine of theta times E sub theta. And what we know is that det dt in t is equal to its magnitude times the principal unit normal. Well, the magnitude is equal to 2 theta dot times En. So this gives me that det dt in t is equal to 2 theta dot times En. So if I substitute that, we obtain the following result for the acceleration. The acceleration of p as viewed by an observer fixed to the track is equal to d dt of the speed times the tangent vector plus the speed times the magnitude of the tangent vector, which is equal to 2 theta dot times the normal vector. So this, if I go back to the original expression, let's recall that the speed was equal to theta dot. That's what I had originally, which means that the rate of change of the speed is equal to theta double dot, which gives me that the acceleration of p as viewed by an observer fixed to the track is equal to theta double dot times et plus 2 theta dot squared times En. And you can see that that's a very simple expression which gives me the acceleration of the of that point P using intrinsic coordinates as opposed to using cylindrical coordinates. Because if I had used cylindrical coordinates to do this problem, I would have had to use a lot of trigonometric functions in order to be able to get the final acceleration, and it would have been a much more complicated expression. This is a much more compact and much more tractable expression from what I would get if I had continued to do this problem in cylindrical coordinates, which I could have done, but it would have required a lot more algebra. It would have been a lot more brute force, and it wouldn't have been so compact in the end of getting the expression that I have here. So now let's study a second example. So in the second example, we have a particle that slides on a spiral. It's a logarithmic spiral. The spiral qualitatively looks as I've drawn, and the position of the point P relative to sort of the center of the spiral is depicted in the figure, and it's defined through an angle theta and a distance r. And in this case, the equation for the spiral is equal to r0 times e to the minus b times theta, where r0 and b are constants. Now, we're going to go through the same kind of procedure that we did before, which is that the objective of the problem is to determine the velocity and acceleration of P as viewed by an observer fixed to the track. And again, we're going to try and do this using intrinsic coordinates. So, as we had in the previous example, there's one rotation in this problem, which implies that we need two reference frames. And these two reference frames are the base reference frame, which is the track, which I'm denoting as T, and then the first rotating reference frame, which is the plane formed by the direction out of the page and OP. So now let's start. T is equal to the track. I'm going to define the origin to be at O. I'm going to put EX along OP when theta equals 0. EZ is going to be out of the page, and then EY is going to equal EZ crossed with EX. The next frame, which I'm going to call A, is equal to the plane formed by the directions out of the page and the direction OP, and the out of the page direction is EZ, so it becomes the EZ OP plane. Now, the origin of the coordinate system is going to be at O. I'm going to put ER along OP, EZ is going to be the same as EZ, and little ez is going to be the same as big EZ, and then E theta is going to equal EZ crossed with ER. So this picture is going to be similar to the picture that was drawn for the previous example, where we have EX, EY, and then ER and E theta. And then EZ is the same thing as little ez. And then the angle is theta. Now, the position of P relative to O is going to equal RER, but R in this case is equal to R0 times e to the minus b theta times ER. So the velocity of point P is viewed by an observer fixed to the track is equal to the rate of change in the track of the position of P relative to O, which is equal to the rate of change in A of the position of P relative to O, plus the angular velocity of A and T crossed with the position of P relative to O. So let's go through and compute the rate of change in reference frame A of the position of P relative to O. Well, because the position of P relative to O is expressed in a basis that's fixed in frame A, this becomes minus R0 times B times theta dot times e to the minus b theta times ER. And that comes from the fact that when I take the rate of change of e to the minus b theta, I get minus b times e to the minus b theta times theta dot, and then I put all that together to get the expression that you see. The angular velocity of A and T is equal to theta dot EZ, which implies that omega AT crossed with the position of P relative to O is equal to theta dot EZ crossed with R0 times e to the minus b theta times ER, which is equal to R0 theta dot times e to the minus b theta times e sub theta. So therefore, the velocity of point P as viewed by an observer fixed to the track is equal to minus R0 times b theta dot e to the minus b theta times ER plus R0 times theta dot times e to the minus b theta times e sub theta. So let's suppose that we rearrange this expression by factoring out all the common quantities. The common quantities are R0, and then we have theta dot times e to the minus b theta, and we're left with minus b ER plus e sub theta. So from this we can actually calculate, we want the tangent vector, right? The tangent vector is going to be this velocity divided by the speed. So let's calculate the speed. The speed as viewed by an observer fixed to the track is equal to the magnitude of the velocity as viewed by an observer fixed to the track. Now, assuming theta dot is positive, because we just assume the angle theta is increasing, this becomes whatever's sitting out in front of this vector, which is R0 times theta dot times e to the minus b theta, times the magnitude of the vector that's in the parentheses, and that's equal to the square root of b squared plus 1. So from this, we now know that the tangent vector, in terms of cylindrical coordinates, which is equal to the velocity divided by the speed relative to the track, is equal to, what's it equal to? Well, if we take the velocity and divide by the speed, the R0 theta dot e to the minus b theta cancels out, and we wind up with minus b ER plus e theta, all divided by the square root of b squared plus 1. Now, if we use that as the starting point, we now can write the velocity of point P is equal to the speed times the tangent vector. Now, I'm not going to carry this expression for the speed through all these calculations. I'll wait until the very end, and we'll do it all. We'll do it all at the end, because I really only need to take that derivative once. There's no need to carry a lot of algebra with us, so we'll just keep it. We know that the acceleration, as viewed by an observer fixed to the track of this point P, is equal to the rate of change in the track of the velocity as viewed by an observer fixed to the track. But the tangent vector is expressed in terms of a basis that's fixed in reference frame A, and we're ultimately going to have to take rates of change of that tangent vector in reference frame A. But for now, let's do this. This is equal to d dt of Vp in t times Et plus Vp in t times the rate of change of Et in t. So now we actually need to compute this rate of change of the tangent vector. So here's what we're going to do. The rate of change of the tangent vector in the track, because the tangent vector, let's look at it, the tangent vector is equal to minus BER plus E theta all divided by the square root of B squared plus 1. So this is expressed in the basis ER, E theta, EZ, which is fixed in A. So this is equal to DET dt in A plus omega AT crossed with E sub t. But DET dt in A is equal to 0. Why is it equal to 0? Well, it's equal to 0 because if you look back at this expression, you'll see that B is constant, so all the coefficients or all the components of this vector are constant, and ER and E theta are already fixed in reference frame A, so that rate of change is 0. The angular velocity of A and T crossed with ET is then equal to theta dot EZ crossed with minus BER plus E theta all divided by the square root of B squared plus 1, which gives me omega AT crossed with ET is equal to, well, let's start taking vector products. EZ crossed with ER is E theta, and EZ crossed with E theta is minus ER. So I get minus ER, when I flip the order, minus B times E theta, all divided by the square root of B squared plus 1. Well, EZ crossed with ER is E theta, and then EZ crossed with E theta is minus ER. So that gives me the that expression, which tells me that the rate of change of the tangent vector as viewed by an observer fixed to the track is equal to theta dot times minus ER minus B E theta, all divided by the square root of B squared plus 1. Now, if you look at the vectors, we can see that the following is true. We know that En is equal to det dt in t divided by the magnitude of det dt in t. So let's compute the magnitude of this rate of change of the tangent vector as viewed by an observer fixed to the track. What's that equal to? Well, that is equal to the following. It's equal to theta dot times whatever the magnitude is of the vector that's multiplying theta dot. Well, the magnitude of the numerator is the square root of b squared plus 1, and the denominator is the square root of b squared plus 1, so that just gives me 1. So this is equal to theta dot, which tells me that the principal unit normal is equal to minus b, so minus ER, minus b E theta, all divided by the square root of b squared plus 1. Now, one thing we can do actually to check to make sure that we did this correctly is that let's suppose we take ET dotted with EN. Remember the expression for ET? It's minus BER plus E theta. So let's actually write this, or divided by the square root of b squared plus 1. Let's take ET dotted with EN. What was ET equal to? It was minus BER plus E theta, all divided by the square root of b squared plus 1, dotted with minus ER minus B E theta. all divided by the square root of b squared plus 1, which is equal to, well, if I take the dot products here, what have I got? ER dotted with ER is 1, and then minus b times minus 1 gives me b. And then the second term is e theta dotted with e theta is 1, and I get 1 times minus b, which gives me minus b, all divided by b squared plus 1, which is equal to 0, which checks out that ET is orthogonal to EN. Okay, that's exactly what we wanted, that they're orthogonal. So that is in fact correct. So now we actually can write that the rate of change of the tangent vector as viewed by an observer fixed to the track is equal to its magnitude times the normal vector. Well, the magnitude is equal to theta dot times the normal vector, because the principal unit normal is the direction of this, and we just said that the magnitude is equal to theta dot. So then, what do we have? The acceleration of p as viewed by an observer fixed to the track is equal to the rate of change of the speed as viewed by an observer fixed to the track times the tangent vector plus the speed times the magnitude of det dt in n, det dt in t times en. And if we actually write that out, we get the rate of change of the speed times the tangent vector plus the speed times theta dot times En. Now, we could substitute in for the speed if you want to. If you recall the speed back from earlier, the speed was equal to, here, r0 theta dot e to the minus b theta times the square root of b squared plus 1. So the speed was equal to r0 times theta dot times e to the minus b theta times the square root of b squared plus 1. So we can differentiate this to be able to get our final expression if we want, or we can just leave this here. But, for completeness, let's actually take the derivative and then substitute everything in. So ddt of vp and t is equal to, well, let's look at this expression. r0 is constant, the square root of b squared plus 1 is constant. So what we get is we get r0 times the square root of b squared plus 1 times the derivative, which is theta double dot e to the minus b theta, and then minus b times theta dot squared times e to the minus b theta. Now, how did I get that? Well, because I've got theta dot and then times minus b times another theta dot times an e to the minus b theta. So the e to the minus b theta comes out of this expression, and we wind up with r0 times e to the minus b theta times the square root of b squared plus 1 times theta double dot minus b times theta dot squared. So that's the rate of change of the speed. Now, we can actually substitute all of that in, and we can get that the acceleration as viewed by an observer fixed to the track is equal to r0 times e to the minus b theta times the square root of b squared plus 1 times theta double dot minus b times theta dot squared times et. And then I've got theta dot times the speed. So that gives me plus r0 times theta dot squared. Well, actually, let's do it in the same order that we have everything else. That it looks similar. We've got r0, and then times e to the minus b theta, and then I have a theta dot times a theta dot, which gives me a theta dot squared times the square root of b squared plus 1, and then times en. And you can see that what we got there is we got r0 times theta dot times e to the minus b theta times the square root of b squared plus 1, and then there's another theta dot, so I get r0 times theta dot squared, and that's how that came into being. And that is our final expression for the acceleration of point P as viewed by an observer fixed to the track in terms of intrinsic coordinates. So in this lecture, we've been able to describe intrinsic coordinates, which, if I go back to the beginning, just to recap, so let's recap a little bit. We described intrinsic coordinates. Intrinsic coordinates have been described. And then we applied the results to two examples. And we basically have shown how to be able to write velocity and acceleration in a particular reference frame of interest in terms of the tangent, the normal, and the binormal vectors. And we've been able to use that information to be able to come up with more compact and sometimes more tractable expressions from what we would have had we just gone ahead and used standard coordinate systems such as spherical coordinates. It's made it possible for us to be able to formulate another way of being able to parameterize motion of a point.